let me start the PCS seminar. Pleasure to introduce our speaker today, Roland Cristopher Caballar.
Caballar, yes.
He completed his PhD in physics from University of Philippines, Diliman in 2009, and he measured the postdoctoral researcher. He said many countries, Korea and the South Africa and the Philippines. Since the 2019, he worked at the University of Santo Tomas as a professor. He's an expert on various areas, like the quantum physics, like ultra-cold atoms, the open quantum systems, and also some medical physics, the radiation physics, and also the radiation dosimetry. He will stay here in the following 2 weeks, and let's enjoy to discuss with him. He's stay at the visitor office, and today he will talk about the driven dissipative dynamics of trapped ultra-cold atom systems interacting with the background BECs. Yeah, welcome our speaker.
Okay. Thank you very much, Dr. Sohon Park, for that very comprehensive introduction. So, ladies and gentlemen, good afternoon. My name is Roland Cristopher Caballar. As stated here in the slide, I am an assistant professor at Anyway, this is the outline of my lecture for this afternoon. So, as you can see, there will be 6 parts, but none of them are of equal length. Some may be shorter than the others. In particular, part 5 should be the longest of the portions that I will present for this afternoon. Okay? But before I actually present my lecture, first, a little introduction to the corner of the universe where I'm from. I'm from a little town called Manila in the Philippines. Okay? And this is my home institution. The formal name is the Royal and Pontifical University of Santo Tomas, but we just call it University of Santo Tomas, or as abbreviated, UST. Okay. Now, a few facts about my home institution. UST was founded in 1611. Okay, 1611 via a donation of books and funds from the late Archbishop of Manila, Miguel de Benavides. Now, at that time, the Philippines was a colony of Spain, so royal permission was required from the King of Spain, at that time King Philip, after whom the Philippine Islands was named. Okay? Hence, the royal portion of the name of the university. At the same time, because the university is operated under guidelines issued by the Holy See in the Vatican, it is a pontifical university. Since 1611 up to the present, the university has been continuously owned and operated by the Order of Preachers, also known as the Dominicans. I'd like to note as well that since its founding in 1611, it has been continuously conducting classes, except for 2 separate occasions. One was the Philippine Revolution from 1898 to 1899. The other was the Second World War, during which time the Japanese occupied the Philippines, and the university campus was used as a concentration camp for foreign prisoners. Okay, that being said, my college, the UST College of Science, was established in 1926 to administer the science, pre-law, and pre-medicine programs at the university. However, I would like to note that before then, these programs were already in existence in the University of Santo Tomas, but under a different faculty. So it was only in 1926 that these programs were established or were organized under a single college for administrative purposes. Now, I would also like to note that the College of Science only administers undergraduate programs. All graduate programs in the university are administered by a separate UST graduate school. So we have undergraduate programs in applied physics, applied math, biology, chemistry, and psychology. We do not have a master of science or a PhD program in physics. What we do have is a master of science in applied physics, major in medical physics program. Now, the College of Science has three buildings. Okay, so the first building is known as the UST main building. Okay, so next slide, please. It hasn't switched there yet. Okay, sorry. So the UST main building, okay, you can see it here. So the UST main building is right there. Okay, so the third floor is used for teaching and administrative offices. And we have two separate laboratory buildings, the Central Laboratory and the Thomas Aquinas Research Center, which is shared with the UST Graduate School. Our research and teaching laboratories are located in the Central Laboratory and in the Thomas Aquinas Research Center. So beyond that, as you can see in the slide, you can see the rest of the city of Manila. Okay, now, with those preliminaries aside, let us now proceed with my talk itself. All right. So, for this afternoon, what we're going to take a look at is what is known as an open quantum system. So, open versus closed quantum systems. Okay, what's the difference? So, closed quantum systems are physical systems that are, as the name implies, shielded or isolated from the environment itself. Okay. Now, the thing is that with closed quantum systems, we are familiar with how they work. We know how to describe them mathematically. You use the old-fashioned Schrodinger equation for non-relativistic systems or the Dirac equation for relativistic systems. Okay, that's for single particle systems. Of course, for many body systems, it's another story. But the point is that for closed quantum systems, you don't need to consider the effect of the environment on it. But for open quantum systems, it's different. Okay? You have to consider the effect of the environment on your system. So there's an interaction between the system and the environment that will affect the system, but it should not affect the environment. Okay? So in this case, therefore, this coupling between the system and the environment can lead to some very interesting effects. Okay, but before that, here are two examples of open quantum systems. Both of them involve atoms either trapped in or passing through optical cavities. So the first as shown in the diagram here, would involve atoms trapped in coupled optical cavities. And due to the interaction between the atoms and the optical field in the cavities here, would result in these atoms becoming entangled with each other. The second is you have atoms passing through an optical cavity that leaks out photons. Okay? So these are just two examples of the multitude of open quantum systems that are currently being studied both theoretically and experimentally. Now, here's the thing. With open quantum systems, this is not exactly desirable because open quantum systems will always introduce what is known as decoherence. Okay? Now, the thing with decoherence is that they destroy the quantum correlations that are crucial to both quantum information protocols as well as for quantum computing algorithms. Okay? So that's why, for the longest time, quantum systems had to be closed rather than open for quantum computing applications. However, with open quantum systems, it has a primary advantage. Okay, that is, if you have a quantum system interacting with the environment, the interaction between the system and the environment would drive that system towards a unique set of steady states. In other words, your system interacts with the environment in such a way that eventually the system evolves towards a set of states that will remain constant with respect to one physical property or one physical variable over time. However, the resulting steady state is dependent on the choice of system and your environment. Okay. I always like to say that when it comes to open quantum systems, they are useful for preparing quantum states. In fact, using open quantum systems to prepare quantum states is analogous to cooking ramen using hot water. Okay? So nowadays, to make ramen, all you have to do is buy that instant ramen from your favorite convenience store, open the packet, pour in the ingredients, then pour in the hot water. Your system is your ramen plus the ingredients. Your environment is the hot water. Pour in the hot water, cover it, set it aside for a few minutes. After that, you have a tasty bowl of ramen to chase your hangover away. Okay? It's the same thing with open quantum systems. Okay? You choose an appropriate system, you choose an appropriate environment, allow both system and environment to interact with each other, and the result is that that interaction between system and environment will drive the system towards your desired steady state. Okay? That is actually advantageous from an experimental standpoint because the other way to prepare quantum states is you do a measurement on a quantum state, continuously monitor it, continuously control it until you get the desired quantum state. With open quantum systems, you don't need that. Yes.
May I ask you a question?
Yeah.
In the previous slide about this, the desired stage, the
Yes.
effect of the environment, give rise to the dissipative effect.
Yes.
The coherence.
Yes.
So that normally when there's a decoherence, you expect your stage in a long time limit followed by the Gibbs distribution, for example.
Yes.
Here it seems that the unique set of stage not necessarily followed by the Gibbs distribution.
Yes.
Right?
That's
still there's a quantum property.
Yes, that's correct. So with respect to some observable or some variable, it will still have certain quantum properties. But yes, you would expect that decoherence would result here due to the interaction between the system and the environment.
Mm-hmm.
Okay. Yeah. So that's for your open quantum systems. Now,
so in the case
yes.
some environment doesn't break the quantum coherence.
Okay, as can be seen here, there are cases wherein you have a system interacting with the environment, but there are certain, how do I say this? As will be shown here, coherence for a qubit, okay, encoded in these atoms would be maintained, okay. But this is actually a particular case. But in general, you would have decoherence or the breaking of quantum coherences with respect to some observables for your state. Yeah. Okay. So here are some examples of dissipative quantum state preparation.
Roland,
Yes.
there is some delays, so we can solve now.
Okay.
10 seconds delays.
10-second delays. Okay.
I'm sorry.
All right, not a problem. Okay. So here's an example of a dissipative quantum state preparation scheme. So this one was formulated by Verstraete, Wolf, and Juan Ignacio Chirac in 2009. Now, for this dissipative quantum state preparation scheme, you have individual quantum particles, and each of them would be locally coupled to a set of environments here. So one particle coupled to this environment and this environment. This particle is coupled to this and this environment, but not that, and so on and so forth. So this dissipative quantum state preparation scheme was quite general, and what they showed was that depending on the choice of your system and the environments to which each particle in the system is coupled, the resulting interaction would drive the system towards a desired steady state. But again, that would depend on what your environment is. That would depend on what your system is. Okay. Next, we have this. Yes.
About this slide, maybe could you give us more details? What was the desired state of this system? Because this is like Nature Physics paper, this should be something important achieved there.
Yes. Fortunately, I have that paper on hand. One moment. Okay, so here, according to the paper, you have some strongly correlated states. Okay, so you have matrix product states. Also, you have one moment. Okay. You're also able to formulate some stabilizer codes that are used in quantum computation. So in this case, they did not specify the specific environment. They did not specify the specific system. So the nice thing about this is that this is quite general. Okay, it's quite general in the sense that sorry about that. Okay, there we go. So it's okay, right. So it's quite general in the sense that you don't specify the specific type of system or the environment, but they did show that for this type of correlation, you would get such strongly correlated systems like those matrix product states, yeah, as well as those stabilizer codes that I mentioned earlier, yeah. However, for a more specific dissipative quantum state preparation scheme, we have this paper by Daly, Fedyshev, and Zoller. So for this one, what they did was that they considered a particular type of quantum system, which are neutral atoms confined in an optical lattice, and they interact with a superfluid. Now, they did not specify if this is a BEC, okay, but they did mention that it's a superfluid. So the interaction between the superfluid and your trapped neutral atoms here would result in excitations being released by your trapped atoms into the superfluid, and that would cool down your trapped atoms here. Okay, and according to the paper, it should be possible as well to maintain coherence of a qubit encoded in these atoms. So in other words, the dissipative process here can be used to cool down these atoms into their lowest possible energy state. Actually, this paper by Daly, Fedyshev, and Zoller was also the basis for these other dissipative quantum state preparation schemes. So we have here the paper by Sebastian Deal and co-authors. If I'm not mistaken, Professor Deal also visited here at PCS IBS before. Yeah.
Sorry.
Okay. Yeah, because I saw his name among the list of visitors there. So according to this paper, okay, it's actually quite similar to the scheme presented by Daly, Fedishev, and Zoller, but instead of simply immersing your trapped or your trapped atoms in your optical lattice in a superfluid, okay, you also introduce optical driving here, okay? So in other words, you have lasers with frequencies omega and detuning delta here that would excite your trapped atoms from these lattice sites here, denoted by R sub I and R sub J, to excited energy levels located here at points between the lattice Rij here, okay? Now, once these atoms are excited to these energy levels at these points here, then these atoms will emit excitations into your BEC in which it is immersed, so that these atoms will then return to their ground state here. Okay? So this combination of driven dynamics together with dissipative dynamics would result in a pure, or in these atoms being described in terms of a pure state with long-range order. So when we say pure state, the place of the density matrix corresponding to these atoms is equal to 1. Okay? Now, it is to be noted that this corresponds to an optical lattice with many sites. Now, a modification, or now another similar dissipative quantum state preparation scheme is shown here. So,
may I ask you
yes.
one question here? What's the role of the background in
okay, the role of the background here, the background BEC, is it serves as a reservoir of the excitations emitted by your ultra-cold atoms as they return back to their ground state. So what happens is this: you have your atoms here, okay? They're trapped at these points in the optical lattice. Then you use a laser to excite them here to these points here, okay? Then, because of the interaction between the trapped ultra-cold atoms and the background BEC in which they are immersed, that these ultra-cold atoms excited here would emit excitations into your background BEC. Okay? So
for example, if we replace or consider the background like a thermal algebra instead of the BEC.
Sorry, Sam.
Thermal algebra, bosonic algebra.
Okay. In bosonic, sorry.
Yeah, bosonic algebra. The thermal algebra instead of the background BEC.
Okay.
As a algebra which absorbs some energy.
Okay.
Can it see some similar?
Okay. That's a very interesting question here, because the whole point why a background BEC was used is because if excitations are introduced into the background BEC, right?
Mm-hmm.
It would or those excitations would be received by atoms in the BEC, exciting some of them. But because the BEC is supposed to be larger in size than the trapped ultra-cold atoms, that should not significantly affect the BEC itself. Okay, so some BEC atoms may be excited, but because it's supposed to be larger than the trapped ultra-cold atoms, not all of the, or a significant number of atoms in the BEC would still remain in the ground state. Okay, so its BEC-ness would still remain. Okay, yeah.
Okay.
So that's why a BEC was used here.
I have a question.
Yes.
The ground state is not talk to the environment.
Sorry. The ground states here.
Yeah, ground state also interact with the
Okay.
state.
Yes. Actually, that's a very good question as well. Yes, there should be an interaction between these ground states here and the background BEC in such a way that excitations should be emitted the other way around, right? So here you have excitations emitted from your atoms to the background BEC. But because of that interaction, that background BEC should also emit excitations here, exciting it, correct? But here, how do I say this? They are sorry. How do I say this? Because most of the atoms are in the ground state, right? Any excitations emitted from the BEC to your atoms in the ground state should be very small and in such a way that it should not be able to excite your atoms here to the excited state. So in other words, it's like any energy difference between the ground state of your trapped ultracold atom gas here and the background BEC should be insignificant. Okay, so that any excitations emitted from the BEC here will not be enough to excite them to the excited state here. So effectively, it's like the only way for your atoms to be excited from here to here is by using your driving lasers to excite them from the ground state here to the excited state here. Yeah. Okay. Also, I would like to note that there is a detuning here of the laser, so that the reason why there is a detuning is it may be that the frequency of the frequency of the photon would correspond to a photon energy that will excite your atom to a higher energy state, which is close to, but not identical to, this excited energy level here. Okay? But nonetheless, it should be close enough such that any excitation emitted by your atom should enable it to go back to your ground state here. Yeah. Okay. This dissipative quantum state preparation scheme was used as a basis for this next scheme that I will be presenting. So for this one, my co-authors in this paper were okay. So how do I say this? There was not enough space actually to list all of the co-authors, but I'd like to mention that my co-authors in this paper are Sebastian Deal, Harry Makela, Marcus Oberthaler, and Gentaro Watanabe. So we formulated a dissipative quantum state preparation scheme wherein instead of using an optical lattice, you have a double well potential embedded in a wide harmonic potential. So similar to the dissipative quantum state preparation scheme earlier, you have your ultracold atoms trapped here trapped here in the double wells. These are excited using lasers with these frequencies emitted here to one of two energy levels of your harmonic oscillator. And by interacting with the background BEC, these atoms, once excited, will emit excitations into the background BEC, enabling them to return back to their ground state here in the double well. Okay, so the result is that the ultracold atom gas trapped here would be driven towards there you go. They will be driven towards a phase or number squeeze state. So when you talk about the phase or number squeeze state, the expectation value of the phase or particle number of the many body ultracold atom state here would have minimal uncertainty. Yeah. So those are some examples of dissipative quantum state preparation schemes that I am presenting here as a background to the talk. Now, the reason why I focused on those dissipative quantum state preparation schemes are due to the reasons that I am presenting here in this slide. Okay. Now, the thing is that with some dissipative quantum state preparation schemes, the environment would be an optical cavity or a photon cavity, and that might not have a multitude of modes or multitude of energies allowed. So as stated in the slide here, the energy spectrum of your excitations can be treated as continuous, allowing for multiple modes of dissipation from one energy state to another. Unlike for the case we're in, if you have a photonic cavity, it may be that you only have a single mode or a single type of, or a single wavelength or single energy that can be or a photon that can be emitted to your cavity there. At the same time, as was shown in the paper by Daly Fedishev and Zoller, it may be the case that if there is a quantum state encoded in an individual atom for a gas of atoms, that coherence may not be destroyed, but rather the dissipative dynamics will cool or lower the temperature of that quantum state. Finally, one can still combine your dissipative dynamics together with optical driving, so in order to create new dissipative quantum state preparation schemes. So you can excite your atoms from the ground state to higher energy levels using laser fields, and at the same time, the interaction between these excited atoms and the background BEC or superfluid can result in those ultracold atoms being or returning back to their initial energy levels or their initial states. So in doing so, this combination of driving and dissipative mechanics will result in your ultracold atom gas being driven towards a unique steady state, which will again depend on the type of system chosen and the type of environment chosen as well. Now, for the main part of my talk,
Sorry, may
yeah.
I
Go ahead.
question? What is the cool? You here the dissipative dynamics that will cool, lower the temperature. If your initial many-bar stage is the ground stage, can you order lower?
No. Yeah, no. This applies to ultracold atoms, which are not yet, or where majority of the atoms are not yet in the ground state.
I see.
Yeah, are not yet in the lowest energy state. Yeah. So most of them may still be in a higher energy state, but by allowing it to interact with your background superfluid, you can cool it down to a lower energy state. Yeah. So with that, okay, so now for the main part of my talk, wherein I am going to describe a dissipative quantum state preparation scheme that I have formulated in order to, or with the objective here being to prepare a quantum state or to prepare a many-body quantum state whose expectation value or whose particle number expectation value will remain constant over time. Okay, so here I have as my trapping potential an array of 5 harmonic oscillator potentials, all of which are adjacent to each other. So in 3 of these harmonic oscillator potentials, there are ultracold atom gas, or there are components of or parts of an ultracold atom gas loaded here. Okay, so part of the ultracold atom gas loaded here, another part loaded here, another part loaded here. Okay, these atoms in these ultracold or these ultracold atoms in these traps are then driven by lasers with frequencies and detuning indicated here in the figure, omega 1, omega 2, and delta 1 and delta 2 respectively, to excited states or to excited energy levels in the neighboring harmonic oscillator potentials. So once they are driven to their excited states in these neighboring harmonic oscillator potentials, these driven atoms will then emit Bogoliubov excitations into the background BEC to enable them to return to their ground state energies ground state energy levels in these neighboring harmonic oscillator potentials as well. So it's like, for example, if you have an atom which is part of the component of the ultracold atom gas, which is here, then because of the laser, okay, the laser here would drive the atom from this energy level and this trapping potential to this excited energy level in this potential here. But because of the interaction with the background BEC, then your ultracold atom here will emit an excitation into the background BEC, and it will return either to this potential here or this potential here. The thing are because for both of these potentials, the ground state energy levels are the same. Okay? So emitting an excitation will enable an atom excited here to return either here, or an atom excited from here to return from here, or to return either here or here. At the same time, atoms trapped here, once excited here, can, by emission of a Bogoliubov excitation to the background BEC, return to the ground state either here or here. Okay?
May I?
Yes.
Here, the larger the detuning parameter, the enhancing some emitting the excitation to BCS. Is there any some condition
For the
related, between this the detuning parameter and the emitting rate of the excitation to BCS?
Okay, this one I have not looked at yet actually. So, but the only thing that we have to ensure here is that the tuning is such that this is close to the excited energy level here. Okay, yeah. So that's the condition that we set at the moment. Okay.
But it could be zero.
Yes, it's possible that it could be zero. Okay. But ideally you'd want it to be excited here, right? But as will be shown later, the magnitude of the detuning would also be crucial in what we call adiabatic elimination, wherein the excited energy levels are, or the creation and annihilation operators for the excited energy levels will be expressed in terms of linear combinations of your ground state energy levels. Yeah. So here is the Hamiltonian describing the system. Okay. This is in terms of your creation and annihilation operators for each harmonic potential, or for each harmonic potential in your trapping configuration here. So we assume that the ground state energies for traps 1, 2, and 3 are equal to each other, while the excited state energies in traps centered here and here, while excited, are also equal to each other. Okay. Now, the system would be immersed in a background BC, which will act as a reservoir of Bogoliubov excitations with the Hamiltonian given there. Now, we assume that the excitation energy would be sound-like in nature. In other words, E sub k is directly proportional to the wave number k here. Okay? To ensure that this is the case, we impose the condition that k over 2 MBC is much less than 1. C here is the sound. velocity in the condensate. Okay, so essentially we're saying that your wave or your wave numbers K here will be much less than C here. Okay, so the result is that the excitation energies would be linearly proportional to K. So under this condition, the resulting interaction Hamiltonian written in terms of the system and your background BEC operators is given by this equation here.
Is the excitation energy
Yes.
already known? I mean, how did you get this version?
Okay, actually this is already this is already known, or it's already given for BEC. Yes. Okay. So for this case, this is our interaction Hamiltonian. Okay. Okay. So the system operator is given here. So your phi's here are your energy eigenfunctions for the ground state and for the excited state. So while they correspond to the same energy levels, their forms are well, there are some differences here depending on where your or which of the three traps these eigenfunctions correspond to. We make use of the condition that for Gaussian functions, okay, so long as the width is narrow or sigma approaches zero, you can write them in terms of Dirac delta functions. Okay, so here the width of your eigenfunctions in the ground state is given by this equation here. So by expressing it in terms of these delta functions, we can simplify the integration over position that we will perform later. Okay, as for the excited states, they would have this form here. Now, it's important to note that because our trapping potentials are harmonic, then the resulting energy eigenfunctions for the ground state and the excited state can be taken to be eigenfunctions for your harmonic oscillator potential. So again, while these correspond to the same energy, their form is different depending on which trap they correspond to. And here, again, the width of your eigenfunction is given by this expression here.
I'm sorry,
Yes.
maybe I missed. What's the nature of interaction between overloads and
The background BEC? Okay. In this case, as I showed earlier, it's here. Sorry.
Oh, I mean, you have constant ASB, mu, what's parameter?
Okay, sorry. So here, okay, M sub B is the mass of your atoms in your background BEC. As I mentioned earlier, C is the sound velocity in your BEC. K is the wave number corresponding to the excitation. Omega sub G and omega sub E later.
No, I'm sorry. Our equation, you have interaction Hamiltonian. You have
This one here.
Yeah.
Okay, sorry.
You have ASB
This-
and mu.
Okay, thank you. So ASB is your scattering length between your okay, here. The scattering length between your BEC atoms and your trapped ultracold atoms. Mu is the reduced mass of your system and the environment here. So 2 pi here is your constant proportionality. Psi S would be your system operator. Psi B would be your background BEC operator.
But I mean, is it Coulomb interaction or what?
Sorry.
Coulomb.
Okay. In this case, how do I say this?
Look, this looks like some sort of short-range interaction, right?
Yes,
Because
that's correct.
all of these psi's have the same x. And so probably you are considering some sort of elastic collision.
Yes, exactly. So it's not a long range interaction. Okay. So it's like particle to particle interaction. Yeah.
So one Bogoliubov excitation is from the term there. It means that essentially one of these Bogoliubov excitation is first annihilated, then the other one is created, and then similarly that's the thing that happens with the system also. So
Yes.
it's like some sort of elastic collision between the
It's a
system photons and the Bogoliubov excitation.
Yeah. So it's like it's a particle to particle interaction. Not long range, not
Oh, but my question is because you can imagine the process when, say, you have scattering of your ultra-cold gases and say you just excite, say, one bogon from condensate. So
Okay.
you consider just, so to say, second order process.
Okay.
Yeah, generally one would consider like the first order process.
Yes, that's the one.
Where like dipole interaction. But this is some sort of higher order process. So
Yep.
But you simply P, but the Bogoliubov has their momentum K. Where is momentum K?
Okay.
Only question independent.
This is for the system. For the environment.
Wait,
Here.
delay.
Okay, there it is. Okay, so that's where the key is. So the operators I gave earlier would be for the system. For the environment, this is where the K will appear. Okay, so U sub K and V sub K are or they're not coefficients, but rather they're functions of K here. So the K dependence is given here. Okay. At the same time, by assuming that the excitations themselves are sound-like in nature, then one can actually simplify this in this form. So E sub K is C times K. This effectively would be much smaller than the rest, so they can vanish. So you have CK minus NBC squared. So L sub K can be written in this form here. Yeah, so that's for the background BC operators. Rho sub B here is the density of the background condensate. B sub K here and B sub K dagger are your annihilation and creation operators for the condensate.
sorry.
Yes,
So going back to Anton's question,
yes.
why are you not writing terms like psi S dagger, psi B plus psi S, psi B dagger? Meaning these are this dipole kind of terms.
Okay. Yeah, actually these are just something like contact.
That I understand, but why are you neglecting the dipole interaction?
Okay.
Because maybe these are neutral atoms or something?
Yes, that's correct. These are ultra-cold neutral atoms. Okay. So they're, how do I say this? They're bosonic atoms, not ions. Yeah. So that's why I'm neglecting all other higher order interactions, and I'm only assuming that they would interact in a particle manner. Yes. Okay. So by the way, also here in the previous slide, I would also like to note that your A's here, AE1, this one here, AE1, AG1 dagger, and so on. These are creation and annihilation operators for your trapped ultra-cold atom gases. Okay, so this is different from your
Last term is position is changed.
sorry,
Previous
this one here.
your last psi S is
This one, psi S, yeah. This is position dependent because of the eigenfunctions here.
why you show the diagram and effect state move to one side to the other side.
Yes.
That means this means some position is changed of the system atom.
Okay. So you're
That means the background has a change of the momentum.
Okay. The thing is that, one moment, where is,
Oh, because
Here.
background is everywhere.
uh,
Yeah, but
Background can
I
only
know
interact.
Kn minus K is
yeah, this one here, here, the key here, right? So, Yes.
Kn minus K.
yeah, so here, e to the ik, e to the negative ikx, yeah. The thing here is that, we are going to treat the background BC as, well, the spectrum later on will be treated as continuous, okay? So, that is a step that I will be, how do I say this, implementing later. So it's like the spectrum of your background BC would be treated as effectively continuous. Okay, yeah. So that's for the background BC. All right. So there we go. At this point, if you substitute the system and background BC field operators here, you'd get this expression, which you can simplify by carrying out the integrations here, as well as by performing later on the sum over your k here. Now, in performing these integrations, you will notice that we neglected some terms here. Okay, so in particular, you will notice that by multiplying this with multiplying this with this, we did not consider terms which are proportional to A and J dagger A and J, as well as proportional to something like A G1 dagger A G3. Okay, here. So the reason why we did not consider that is because when we will evolve this when we will evolve this Hamiltonian over time, and when we will consider when we will be deriving the master equation, effectively the particle number operators for example, AG1 dagger AG1, AG2 dagger AG2, and so forth, those terms proportional to those number operators will effectively vanish, okay? And we are left only with these terms here. So by substituting the explicit form of your energy eigenfunctions here, okay, and carrying out the integration in this manner, and also by using the simplified form of the ground state eigenfunctions, wherein they can be written in terms of Dirac delta functions, you get these integrals here. Okay. Again, by performing these integrations, the result is that your interaction Hamiltonian will have this form. Now, in obtaining this interaction Hamiltonian, this approximation will be used. Our basis here is that with this condition here, our k is much less than 1, and at the same time, to prevent interpotential tunneling, we assume that x sub 0 is much greater than 1. So this multiplied by this, therefore, you should get a term which is also much less than 1. So therefore, this is effectively approximately equal to 1, so that we can neglect those exponential terms here, and we end up with this Hamiltonian here.
Sorry.
Yes.
In your interaction term, you had a psi b dagger psi b.
Yes, correct.
You had a quadratic term. But
yes.
you end up with linear in the interaction. How?
Okay. In this case, we neglected those terms BK dagger BK. So we did not consider those second order terms in for your interaction with the condensate.
Why?
Okay. That's actually.
And where did you neglect it?
Okay. In this case, okay. If you have BK dagger, okay, if you have BK dagger BK or BK or BK dagger, well, that would be that would correspond to just your particle number term, right? BK dagger, and BK would correspond to the number of atoms in the condensate continuously increasing or decreasing. So we want to conserve the particle number inside the condensate, so to speak. So any variations in the particle number in the condensate should be very small as to be negligible. So that's why we only consider the first order terms here.
My question is, how did you get the linear order in the first place? Because you had a quadratic term in your interaction.
Yes. Sorry, this one. Wait, where's that?
Is a condensate density term also.
Yes.
It's an interaction with the ground state of the condensate.
In this Hamilton?
Psi operator. of the
Okay,
Okay,
okay.
next slide, psi is condensate density
got it.
plus correction.
Okay, this one here. Okay. This one. Psi B dagger, psi B. Okay. Yeah. One moment.
Yeah.
Not yet. Okay, there we go. Okay, yes. I see that. So you should, okay, the full term here should be rho, or if psi B dagger psi B, it should be rho B plus, well, you'd have this one, rho B times delta psi B plus delta psi B dagger, you'd have that, plus delta psi B dagger, delta psi B. Okay, yeah. So this term here, delta psi B dagger, delta psi B, would correspond to continuous creation or annihilation of your how do I say this, of your condensate atoms. But yeah, we assume that those terms are negligible. Okay. As for this rho B, well, this would be constant over time, so you can neglect it as you evolve the interaction Hamiltonian over time. Okay. So,
But coming back to the second order processes,
yes.
For certain systems, second order scattering in terms of Bogoliubov can be quite important.
Okay.
I mean, yeah, first of all, it can depend on temperature, as you said, because it's proportional to the number of particles.
Yes.
But plus scattering processes with the creation of the Bogoliubov.
Okay.
I mean, sometimes it's very important because contribution can be larger than the first order.
Okay.
Like this.
Okay. Actually, okay. In earlier iterations of this work, I tried looking at that BK dagger, or BK dagger. But the thing is that, well, because we're assuming that the particle number is constant, I thought of dropping it. But yeah. Okay, that's a very good observation. Thank you for that, Anton, right? Okay, thank you. So this one I definitely will consider for future work. Yeah. Okay, so with that, okay. Sorry, I skipped. There you go. So having derived the interaction Hamiltonian, we evolve it over time using your using the Baker-Campbell-Hausdorff identity, as well as following the commutation relations for the system and the background BEC and annihilation operators to get this form of the time-evolved interaction Hamiltonian. Okay. Once you already obtain this time-evolved form of the interaction Hamiltonian, next step would be to use it to derive the master equation. So here we make use of the Born-Markov approximation. Again, we are assuming that, or for this approximation, the system and the environment are weakly coupled to each other, and that any effect by the system on the environment will have or will not affect the environment greatly. Although effects by the system on the environment or by the environment on the system would affect the system greatly. So this is the resulting form of the master equation into which we can substitute our time-evolved interaction Hamiltonians. Then, once you substitute the interaction Hamiltonians, perform the commutation relations, carry out the integrations over time, and the summation over the k variable, you should be able to obtain the master equation describing the system. Okay, here you go. Now, we note that in carrying out in evaluating the master equation, you also have to evaluate traces over the background BEC variables. So here we use these trace identities here. Okay. Now I would like to note that this is not exactly equal to 0, but we set it effectively equal to 0. Okay, same with this, same with this. But the reason why we set these 0 is, first, we ensure that there will be no excitations emitted from the background BEC to the trapped ultracold atom gas to couple our ground states and excited states. Okay. At the same time, we are going to ensure that the particle number of the background BEC would effectively remain constant. Okay. So in other words, what we will only allow would be emission of excitations from the trapped ultracold atom gas all the way into your BEC. So if, using these trace identities, each trace for each term in your master equation would now have this form. Okay, there are 4 of them: 1, 2, 3, and 4. Okay. Now, once you have obtained the trace, once you have computed these traces, we perform adiabatic elimination to express all creation and annihilation operators for your excited state as linear combinations of the creation and annihilation operators for the ground states as well. Okay? And here now emerges the importance of your delta. Okay? So a non-zero delta will ensure that you can do adiabatic elimination to express the excited or the annihilation operators for the excited states in terms of this linear combination here. Now, this will allow us to express each of these terms solely in terms of the ground state annihilation and creation operators. And finally, once you carry out the integration over time and carry out the integration over or the summation over k by effectively treating your sum over k as a continuous integral over k instead, you get these terms here, which you substitute back in the master equation. And if we introduce this, following previous work, I call this a quote-unquote jump operator, which is essentially a linear combination of these two terms. By the way, epsilon here is a coefficient. Epsilon is omega 1 over delta 1 times delta 2 over omega 2. Okay? So in other words, it's proportional to the ratio of your laser frequencies and your detuning. Okay? So
you mean if you define the jump operator like this, your master equation map into the Lindbladian.
okay. Actually, that's what I'm going to get to next. Okay. Because with this and this is the master equation. Sorry, there. There you go. Okay. So yeah, here's your Lindblad. This is in Lindbladian form. However, there you have this term here, and you have these two terms here as well. Okay. Now, how do I say this? Without these three terms, you'd expect simple Lindbladian dynamics here, right? Simple dissipative dynamics. But the problem here is that you have these two terms here, these three terms, this, and this, which would introduce some complications to our system, which I will show now in my results. Okay, so for the time evolution of our states, I am going to assume that the initial state of the system can be expressed in terms of a linear superposition of particle number eigenstates for or in each of the three harmonic potentials where your ultra-cold atom gas is trapped in the ground state. So you have these here, okay? So Ng1 corresponds to a particle number eigenstate, or for the first of your 4 particle number eigenstates in trap 1. Then this one is Ng21 corresponds to the first of your or the first of 4 particle number eigenstates corresponding to trap 2, and the same with the third case. So we have 3 cases to consider here. Case 1, wherein the expectation number of your particle number in the first trap is greater than the expectation number in the other 2. The second one, expectation value of the particle number in the second trap is greater than the expectation value in the other 2. The third one is where the expectation value of the particle number in the third trap is greater than the other 2. Okay?
Sorry,
Yes.
what this number stands for example, G is one,
Okay.
1.
Okay, so this is the particle number eigenstate for
eigenstate.
particle number eigenstate for trap 1.
Trap
The
one.
first one, okay?
Yeah.
Because you're taking 4 of them, okay? So it's like you're taking a superposition of 4, okay, to come up with, or you're taking a superposition of 4 of these eigenstates to come up with, or to come up with your initial state in trap 1.
Sorry, the number outside this, the parenthesis that indicates the trap.
No, this one here inside the parentheses indicates the trap number.
Yes,
This one indicates eigenstate number.
eigenstate.
So it's like first eigenstate, second eigenstate, third eigenstate, fourth eigenstate. So
Degenerate eigenstates.
sorry. Here, yeah, degenerate in the sense that they all correspond to the same energy level, but different particle numbers. So it's like, okay, if you go back to the initial state, it's like we're saying that you have a different number of atoms loaded in trap 1, different number of atoms loaded in trap 2,
Yes.
different number of atoms loaded in trap 3.
Mhm.
But because we're considering 4 of these states, it's like you have one system, okay? One system, 3 traps loaded. Second system, 3 traps loaded. Third system, 3 traps loaded. Fourth system, 3 traps loaded. Okay?
I see.
Yeah. So in
You suppose the different ground states, different configurations.
yes, correct. But in this case, how do I say this? For all 4 states, the first trap has more atoms than the other 2.
I see.
Yeah. So that's for our initial state here.
But the different number of initial states should be orthogonal to the stage with the different particle number. That do they suppose?
Sorry.
Can you suppose some different configuration of the stage with the different number of?
Okay. So essentially, it's like how do I say this?
For example, in a quantum data, as far as I know, the initial stage with the 2 electrons and the 3 electrons, they cannot be supposed.
Yes.
Right? Because they have different electron numbers.
Yes.
So for this region, I think it's not quite clear that you suppose that the stage with the different number of.
Okay. In this case, again, it's supposed to be a bosonic or bosonic atom gas.
Yes.
Yeah.
So you think it's the possible to.
Yes. I believe so. Yes. Yeah. So in this case, using this superposition and by evolving the state over time. Okay. So here are here are the results. So for this particular configuration, okay, we're in the eigenstates or the eigenvalues corresponding to the eigenstates used have these values. The resulting particle number expectation value for the initial state is for N1, it's supposed to be 500, N2 expectation value is 50, N3 expectation value is 50, and the sum of the particle number expectation values for the initial state should be 600. Okay, now here's the confusing part. Okay, so what I did was I evolved my system over time using the master equation that I derived earlier. Then I computed the particle number expectation values in each trap for trap 1, trap 2, and trap 3. Now, these are the manner by which these expectation values evolve over time would remain the same qualitatively. Even if you or even if there are more atoms in trap 2 or trap 3. What is surprising here and what that I find rather confusing at this point is, if you'll notice, the initial particle number expectation value here was 500. It increased to something like 518 or 519. Okay? At this point, I don't know why that is yet. Okay? So what I did was I took my initial state, evolved it using the master equation, plotted the expectation value of the particle number in each trap over time. This is what I got. Okay? Yeah. This one I'm still trying to figure out why this is the case. To make things more confusing, but if you change the if you change the states used, okay, for the superposition, for trap 1, the steady state expectation value also changes. Okay, and the manner by which they evolve over time would also change. Okay, from this to this and all the way up to here. Okay, while yes, you still have a steady state here. Okay, that's fine. But the thing is, again, the steady or the expectation value corresponding to the steady state changes. Okay, it changes as you change the configuration of your or of the components for your initial state. Now, for the case we're in, there are more atoms in trap 2 than traps 1 and 3. Okay. Given this configuration, the resulting time evolved expectation value of particle number looks like this. While supposedly this increases, but as you can see, the increase is not that significant. For this, the decrease is quite significant. And for this one, it's as if the steady state value, it oscillates, then becomes constant over time. And changing the configuration of your initial state does not change qualitatively the manner in which your states in trap 2 will evolve over time. So it will still decrease until it reaches a steady state value. But the steady state value changes as the configuration here changes over time. As the configuration here changes. Okay, and finally, for case 3, wherein you have more, wherein you have more atoms in trap 3 than in traps 1 and 2, as shown here. Well, you'd still get the same qualitative behavior for the time evolution of your particle number for traps 1 and 2. And in this case, the increase is very small. The decrease is quite small. As for this, it will still oscillate, then approach a constant value. But the amplitude of oscillation is larger compared to the previous 2 cases.
So
Yes,
could you go back to the previous one?
sure. And this one.
Yes. Could you explain what this NG1 parenthesis 1, these things are?
Okay.
What are these numbers do?
Again, this is the eigenvalue corresponding to the particle number eigenstate that is used to form your initial state.
Sorry, so
for each
you
trap.
have 5 traps, right?
Yeah, 5 traps, correct.
And so G1 meaning you are considering the first trap.
Yes, that's correct. Yeah,
And then this trap is a harmonic oscillator.
correct. Yes.
So it will have different n values.
No, it's like I'm considering 4 different realizations. Okay, so it's like I'm superposing 4 different states here. So wait. Let me go back to this slide here. Wait, where's that? Oops. There, okay. So here, NG1, that corresponds to the first, how do I say this? The NG1 corresponds to the first particle number eigenstate, okay, in trap 1. NG12 corresponds to the second particle number eigenstate in trap 2, and so on and so forth, okay? So essentially, I'm considering a superposition of 4.
You have 4 different types of particles.
No. 4 different,
configuration.
sorry. So it's superposition, yes.
different number of state, superposition of the different number of the trap.
I think the total number of particles are the same, but different cases means that, for example, trap 1 you have more particles, but and the less particle numbers in the other traps. But the total number of particles are the same for all cases, and you suppose that
Yes.
these different configurations.
Yes.
I see.
Okay, so yeah, so essentially there it's a superposition of states. Okay, now going back to the results. Okay. Actually that was the sorry. That was the last case that wait, let me resume that here. One moment. Here. Okay. No. Okay. So this there we go. So this is my second to the last result. And by varying the composition of the component particle number eigenstates for trap 3, one would see a variation as well in or in the time evolution of those or of the state in trap 3. Okay, so in particular, this here shows that the particle number or the expectation value of the particle number in its steady state increases, while this here shows that it will decrease or if not remain almost the same as its initial value. Again, why this is the case, I do not know. Okay, this one I am at a loss to explain why. Okay, so in conclusion, for the first trap, okay, there is an increase of particles as it evolves over time. As for why, this is a question I cannot yet answer. Okay? But at the same time, there seems to be a steady state or a dependence of the steady state value of the particle number expectation value on the particle number eigenstate components. And by changing each component, there would be deviations from the characteristic time evolution. But it is this question that I still am at a loss to answer. Okay? Honestly, I don't know why that is the case yet. Okay? Yeah. So, by the way, before I conclude, this is not yet a published work. Okay? So this is I'm how do I say this? This is where my current research is at this point. Okay. Now I am going to try to answer this question, why, as well as try to figure out other details regarding the system. Also, the comments and questions raised here were very useful, and I'll be considering that as well in trying to improve this work. Okay. So that ends my presentation for this afternoon. Thank you everyone for listening.
So the question.
Yes.
You based on the approximation, you make a best equation. Do you check the some condition of the total density of the matrix has a trace is a conjugate, and all density metrics become a positive? There are some conditions used.
Okay.
Do you
Yes.
check this master equation is
Okay.
satisfied this
Okay.
condition?
That's a very good question because at this point, yeah, I did not yet check that condition. So yeah, it should be that the trace of the density matrix should be 1, correct? Yeah. So this one I definitely have to check as well. Not just the trace, but also whether it would actually be constant or something like that. Yeah.
But
Okay, so
there's a dissipative environment. So if your steady state is the mixed stage, then the trace could be less than 1.
yes, but it might, yeah, because again, it's it does have dissipation involved here.
Yeah.
Yes.
If more questions, then let's thank us. Thank you very much.